Hello, so this is the course for 300DF Bilingual of Tuesday, 26th of May. So as I said, I have changed the course. I have extended it because normally I don't get to do that in the third year, but this year I can, okay? And so it's from page 7. Actually, if you print it, it says page 8 for some reason. Last time we saw the Laplace force. You remember the Laplace force? It was a force which, let me take a piece of paper. Okay, the Laplace force, it was a force, you remember that? It was the current times the length of the conductor times the magnetic field, okay? And if you write the law in the complete form, in the vector form, then you have a vector product between the length of the conductor oriented in the direction of the current and the magnetic field, okay? So if we have one current I flowing in this direction, we are going to have our L, the length of the conductor, in that way. If the magnetic field, let's say, is pointing up, in which direction is the force going to be? Do you remember that? You remember it? We did that last time. And the law was this. Okay, so if you want to decide about the direction of the force, you should point your finger in the direction of the current, in the direction of the length of the conductor. Your index, your middle finger in the direction of the magnetic field, and the force is given in the direction of the thumb. Okay, so now I will orient all this like this. So the current to the right, the magnetic field upwards along the page, and so the force is given by my thumb. It comes up. So here we are a force which is pointing up towards us. Okay. So now I want to use this fact that we learned to try to derive in a very simple way the magnetic field due to one conductor, due to one current. Okay, so from that, for that, we will start from a situation which is a bit more complicated, which is the situation of two currents flowing in the same direction in parallel conductors. So you have one wire here which is connected to a generator. You have another wire here which is also connected to a generator, and you have currents I1 and I2 which flow in these conductors. Each conductor creates a magnetic field, and this magnetic field exists so in the location of the other conductor. Okay, so on this image what you see is the current 2 creating a magnetic field. The magnetic field vectors, you will find them here, and they are tangent to these circles. Okay, and so in particular here we will have a magnetic field which is going, well, be careful about the drawing because this is horizontal, so this magnetic field actually it's going in like that. Okay, it's not going up. If it was going up, there would be no effect because it would be parallel to the current. Okay, so here the magnetic field is going in. Okay, and so we said the magnetic field is represented by the middle finger. The current is given by the index, so I have to turn my index down, so it's a bit complicated because of the way I'm sitting. And so in that case, the force is given by your thumb, and the force is therefore in this way. Okay, so this is the situation when you have two conductors with currents parallel to each other. There is actually a force between the conductors. Okay, so this conductor is attracted towards the other conductor, and since the situation is symmetrical, this conductor is also attracted towards the first. So the two conductors, they feel an attraction between them. This is something you maybe didn't imagine, and normally we do the experiment in class but here I cannot do it. I don't have what it takes. Okay, what you do is you just take two cables. You take two cables which are vertical. Okay, they are not very tense. You have your two currents running in these wires, and when the current is running, the wires, they deform a bit like that, okay, because there is a force which attracts them to each other. And in the opposite situation, when you have one current coming down and the other current coming up, then the wires repel each other. We are not going to analyze this in detail. So there is a force which pushes the conductors away. Okay, so between two conductors, there is a force which exists. And this force, we can see experimentally how it looks like. Okay, experimentally, it's pretty obvious that the force, first of all, is proportional to the length of the conductors which are parallel. Okay, the longer the section of conductors which is parallel, the bigger the force, because each element of the conductor produces a certain force. Okay, so you have here the length of the conductors in the numerator. Then, of course, when you increase the currents, the force should increase, and this is something you observe experimentally. So up here, you have the product of the currents. And this is divided by the distance, because, of course, the force is going to decrease when you move the two conductors away from each other. And then there is a numerical factor. There is this mu which comes here. Please accept it like this. If you want me to go into details of that, it's going to take weeks. So there is a factor here, which is a bit, in some way, the equivalent of the G for the gravitational force and of the K for the electrostatic force. But you see here it's a mu, and this mu is called the magnetic permeability constant. So it expresses the way in which the medium in which you are lets a magnetic field develop, if you want. Okay. So let's just compare for a minute. It's not a good comparison, but let's compare this for a minute with the electrostatic force. The electrostatic force is given between two charges Q1, Q2. It's given by K Q1, Q2 over D squared. Okay. Here you see something which is a bit similar. It's not very similar. But what you notice, and I would like you to notice this very clearly, is that here, instead of charges, we have currents, okay? So magnetic forces, they are generated by currents. Magnetic fields, they are generating by currents by moving charges, okay? The currents are the sources of the magnetic field. And the decrease, according to the distance, it's not in D squared, it's in D, but this is related to the fact that we have long cables. Okay, enough for that. So these values of mu, they change according to the medium that you are in. So if you are in the vacuum, the value of mu is 4 pi 10 to the minus 7. But if you are in some substance, like iron or steel, then the constant is much bigger, okay? And so you can modify the properties of any device that uses this kind of force by putting it in a medium which is not air, but which is something else, okay? We will see later examples of that, okay? So here we have an expression for the Laplace force between two conductors. But we know that the Laplace force is also given by this expression. This is the Laplace force acting on wire number 1. So it's the current flowing inside wire number 1 times the length of the wire number 1. This is the ILB formula. Times the magnetic field B2, because the magnetic field which influences the wire number 1 is created by the wire number 2. So this magnetic field, I should call it here B2, okay? And so I have this expression which comes from the Laplace force, and I will take sine which is equal to 1 because the angle is 90 degrees. Now, if you take this expression and you match them together, okay, they express the same force, so they must be equal. So that gives you mu L I1 I2. I take this expression over 2 pi d. And this has to be equal, since the same force, to this expression, which is I1 L B2, and the sine of alpha is 1 because alpha is 90 degrees. Well, what do you have here? I1 cancels, okay? The length cancels, and so now you are getting an expression for the field B2 given by the current I2, and this expression is here. B2 is equal to mu I2 divided by 2 pi d. Okay, B2 is mu 2 pi over 2 pi times I2 over d. This is a general expression for the magnetic field created by a current I2 if you are standing at a distance d from the conductor and if you are in vacuum. Okay, so this is a general law. It's formulated now for the current B2, for the current I2, and it gives the magnetic field B2. But if we generalize that to a current I, then we find this law, which gives you the magnetic field at a certain distance of a wire as a function of the current. Okay, so this, how should we understand that? As I already said before, the magnetic field is kind of turning against around the wire. Okay, so let's say you have a current here. Let's say the direction of the current is this. How do you determine the direction in which the magnetic field turns? Well, you determine it with another type of right-hand rule. Okay, I repeat, you have to use your right hand. Okay, if the current goes in that direction, you put your finger in the direction of the current, and the direction of your fingers, they will tell you in which, how the magnetic field turns around the cable. Okay, current in this direction, the magnetic field turns like this. Okay, so it's doing this. And if you want to show clearly in which direction it is turning, you have to do this. You have to interrupt the circle here so you know that the circle is passing behind the wire, and you can understand that properly. Okay, and then your magnetic field at any point is going to be given by a vector which is tangent to the circle. Okay, at any point around the wire, this magnetic field will have a different direction, and the direction is given by the tangent to this circle. Of course, this circle is a construction of the mind. Okay, there are an infinity of circles like that, if you wish. At any point in space, you have a magnetic field with an intensity which decreases with distance and with the direction which is always tangent to a circle. So these magnetic fields, they are always perpendicular to the wire. Maybe you don't realize this very well on that drawing. So let me do the drawings from above, for instance. Okay, let's imagine I have a current I here which is flowing upwards. How will the magnetic field look like? What do you think? We have a current coming up. So if I look now at the wire from up, I can draw circles around this wire, and the magnetic field, sorry, it turns in that direction. My thumb is up because the current is going up. So the magnetic field turns like this. So what I did here is just wrong. Okay, it doesn't turn in this direction. It turns in the opposite direction. Okay, like this, right? And if I do a circle which is a bit further, then the values of the magnetic field are going to be smaller. The intensity is going to be smaller, but the arrows are still going to be tangent to the circle. And so all these arrows, you see all these magnetic fields, they are in a horizontal plane. They are on the plane of my sheet of paper, and the current is coming up from the sheet. So the magnetic field in this case is always perpendicular to a vector which goes in the direction of the current. Okay, you got it?
Yes.
Good. Okay, now what can you do with a wire? Let me take a wire. Let me take a wire. I have lots of wires on this desk. Okay, let me take this wire. Let me go a bit up with my camera. Okay, so I have a wire here, and if I assume that the current is going in that direction, well, you don't see it very well. The current is going to the right. So if I put my thumb in the direction of the current, it means that the magnetic field is turning that way around the cable. Well, the magnetic field is not moving, okay? It is on circles around the cable. So sometimes I say the magnetic field turns. It doesn't really turn, okay? You understand? It is all around the cable in a direction perpendicular to the cable and tangent to the circles, okay? So here the magnetic field goes down, here it goes down, here it goes down. Now what happens if I take this wire and I make a loop? What happens? Well, the current is going that way, okay? So here the magnetic field produced by this little area is going to go down. The magnetic field produced by this little area is going to go down. The magnetic field produced by this little area is going to go down. So every area on this loop of cable is going to give you a small magnetic field which is pointing down. And so the total on the loop will be a net magnetic field which is pointing down, okay? So this is a way to increase the intensity of the magnetic field by taking an electric cable and putting it on a loop, okay? And then, of course, if you want to make this more intense, you do 2 loops. And if you want to make it more intense, you do 3 loops and 4 loops and so on. And you can do 1,000 loops if you want, and 1,000 loops will give you inside the loops a magnetic field which is 1,000 times stronger than if you take just 1 loop, okay? And this is something we use very much in electronic. This is why we construct coils in electronics, the bobine, okay? Bobine is called coil in English. It's also called a solenoid. Even in French, the word solenoid exists. A coil or a solenoid is basically an electric cable that you have rolled around some cylinder, let's say, some shape, and in this shape you can have vacuum, or you can have some medium inside which will change the value of the constant mu, which we talked about before, and so it will make this element stronger, okay? So if I look at this loop, when it's if I look at a coil which contains many loops, every point on the coil will contribute a magnetic field, and all these contributions, they all go in the same direction, okay? So in the end, you can have an intense magnetic field inside the coil, and the magnetic field lines are going to reclose outside the coil, but they are much less dense outside the coil. So clearly you have an intense magnetic field inside the coil, and you see that this magnetic field is homogeneous, okay? This is what happens in electronics in this type of component that you may have seen if you have opened up a computer or anything else. I mean, it's full of them, okay? Because electronics, what do you use to do electronics? You use resistances, it's very good. You use coils, bobine, and you use capacitors. And with that, you can do an incredible amount of things by changing the values of these components and by putting them, assembling them either in series or in parallel. This is the basis of analogic electronics. Okay, good. So we have this wire, this coil, and we have a magnetic field inside. Let's check with our rule that the direction is correct. Okay, here you don't see it well. Here we have the plus. Let me check. Yeah, I cannot read very well, but I think it's like that. Here we have the plus and here we have the minus of the generator. Okay, so the current conventionally is going in this direction, from the plus to the minus. I recall you that when people first discovered this, it was in the 19th century, they had no ideas of the existence of electrons. Electrons have been discovered at the beginning of the 20th century. So for all the 19th century, the current was studied as a phenomenon we didn't really understand. We didn't really know at the microscopic level what the hell a current would mean. But we knew we had this notion of a current passing from the plus to the minus of the generator. Okay. Now, if a current passes here in this piece of the wire here, okay, the current is going this way, so the magnetic field is going up. And so this is correct. All the pieces of the wire contribute a small magnetic field all over the coil. And so inside the coil you have this net magnetic field, which is very intense. Okay? So that was just to show you another application of these coils. I can also give you the formula. I'm not going to derive it. It's a mess to do that. Well, if you want to do that, you need to take OS physics, and in the 4th year, we do all that in details. Okay, the 4th year of physics OS is specialized on electromagnetism. So we do electromagnetism all year round. So the magnetic field inside this coil, it's interesting to interpret the formula, is given by what? Okay, there is the mu, the constant of magnetic permeability, which comes always in this expression for the magnetic fields. Then here you have the number of loops. Okay, here you have a number of loops. You have 1, 2, 3, 4, 5, 6, 7. Okay, here this is a coil with 7 loops. Okay, the more loops you have, the more powerful the magnetic field will be. If you double the number of loops, the intensity of the magnetic field will double. Then, if you increase the current, the magnetic field will increase too. So you have N times I in the numerator. And in the denominator, you have 4R squared plus L squared, where R is the radius of the coil, okay, from the center to the outside of the coil. It's the radius of the coil, and L is the length of the coil. Okay, this is the general formula. And what people do generally is that they do approximations for 2 special cases. One case is the long coil. The other case will be the flat coil. The long coil is what? It's a coil which is long, which is much longer than its radius. Okay, so for such a coil, we can assume that the length of the coil is much bigger than the radius of the coil. Okay, what implications does this have on this term? If the length is much bigger than the radius, then this term here you can neglect it because it's going to be much smaller than that term. Okay, so you throw away this term, you are left with this one, and it's a square root of L squared, so it's L. This is why for a long coil you obtain in the end this formula. The magnetic field inside is mu times the number of loops times the current divided by the length. Okay, and now if you take the other limiting case, is a flat coil. So what is a flat coil? It's a coil which is very big. It has a big radius, but it has the length. I mean, the length here would be the depth of that drawing. The length is very short. Okay, so in that case, the length is much shorter than the radius. And you go to that expression, You say, okay, the length is much shorter, so this I will neglect. I will keep only this term, and I take the square root of that. The square root gives me 2r, so I have the formula here for the magnetic field inside a flat coil. It depends also on the number of loops and on the current, but it's divided by 2 times the radius. So if you increase the radius, you decrease the magnetic field, which is pretty obvious. Okay, and here, for the same number of loops, if you increase the length, you will also decrease the magnetic field. So if you want to have a strong magnetic field, you should do a lot of loops on a distance which is not too big. Okay. This was just to show you an example. Okay, I'm not going to do anything very special with this. But what you should remember from that is that if you have a current which is running on a loop, okay, let's say we have a current here, so you can decompose this current into elements, okay, and each element is going to give you, in this case, a magnetic field which comes up. So you are going to have a magnetic field directed upwards inside any current loop. And this is the essence of what I'm trying to tell you. So you should frame this and put it somewhere. Okay, this is the essence of what I'm trying to tell you. A magnetic field is created by a current. And the simplest current you can imagine is a loop. Okay, I didn't put the generator here, it's an image. Okay, you have a current running in a loop, you have a magnetic field inside. And now this loop, if I look at it from the side, okay, let's admit that this loop is horizontal. How is this going to look? How is the magnetic field going to look? Yeah, in the center is going to point up. Okay, but what is it going to do then? It's going to come, as soon as you leave the center, the magnetic field lines, they are going to go like this, and they are going to come back from the back. Okay, you remember these drawings of magnetic fields that I made you do, of electric fields which I made you do. Now we are doing the same type of drawings with magnetic fields. Okay, and so we have a geometry of magnetic field around the loop, which is a dipole. Okay, it's the same as the magnetic field of the Earth. It's the same as the magnetic field of a magnet. So you can produce a magnetic field with a current. Maybe it's not completely obvious to you, so let me do some more drawings to recall you that. You remember when we have a magnet with the south and the north, we have magnetic field lines which go from the north to the south. Okay, this is the definition of the magnetic field lines. They go from the north to the south. This is the magnetic field of a magnet. Now, what if I take the magnetic field of a current? Okay, here I have the same current that I was drawing before. Well, here too, you are going to have a magnetic field which has this shape. Okay, and the magnetic field lines, they close outside the ring. Okay, so a loop of current is equivalent to a magnet in terms of creating a magnetic field. Okay, try to remember this because it's something important. Now the details of the calculation of the magnetic field inside a coil, this is less important. Okay, so now if you have this image in mind, now you can understand how a magnet works. I will not go into details because if you want to go into details, again, it's a mess. Okay, it's a 500-600 pages book if you want to study that. Okay, what do we have in a magnet? In a magnet, we have atoms. Okay, so atoms, it's a nucleus with some electrons which turn around it. So let's forget the electrons which are inside, which are attached to the nucleus. Let's maybe look at the electrons which are on the outer layers. And imagine that these electrons are turning on orbits like the planets. It's not the case, okay? At the microscopic level, the electrons do not behave like planets, but we can make a model in which electrons move like planets, and this model has a certain capacity to predict things. So we have electrons which move on circles. An electron moving on a circle, how is that related to a current for you? You remember the definition of the current? It's delta Q over delta T, right? So if there is one electron which is turning in a circle around some nucleus, that is equivalent to a current, because it's a charge which is moving on a certain trajectory. And a charge which is moving is just the same thing as a current. A current is a motion of charges, okay? So every electron inside matter is equivalent to a small current. And when there is a current, what do we have? Ta-da, 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 ta-da. When there is a current, what do we have? We have a magnetic field, okay? So here, be careful, now it's an electron moving this way. So this is equivalent to a current which is moving which way? If I draw here the corresponding current. Sorry? The opposite way, because the current, by definition, goes in the direction of motion of positive charges. So you can see negative charges turning in one direction as positive charges turning in the opposite direction, okay? And so this is equivalent to a current turning in that direction. And if the current turns in that direction, then at any point, the magnetic field is pointing down, so you're going to have a magnetic field attached to every atom due to this current. Okay? Isn't that amazing? It is absolutely amazing. So now imagine your matter, okay? And inside the matter, you have the atoms, okay, and their electrons are all turning on trajectories which are different, okay, and maybe they turn in different directions. So now, okay, here we have a magnetic field which is maybe coming up this way. Here we have a magnetic field which is coming up straight. Here we have a magnetic field which is coming up this way. Here we have a magnetic field which is coming up this way, kind of. Here, it's coming, well, whatever, up, okay? So you understood what I want to mean is that in ordinary matter, I mean, well, not in all substances, but in many metallic substances, you have small magnetic fields which are attached to every atom, okay? But since the direction of motion of the electrons is random, all these magnetic fields, they add each other, they add up, okay? And finally, the net magnetic field inside matter is zero, okay? Now, what happens if you put an external magnetic field on a piece of matter like that? Okay, you take your piece of matter, you put a magnet next to it, and let's say you have a magnetic field, an external magnetic field inside the matter. Well, the effect of this external magnetic field, I'm not going to go into all details, but the effect of this external magnetic field is to align all the small magnetic fields inside matter, okay? It aligns them. So if you put an external magnetic field, the internal magnetic field is going to be changing, and then you have different types of substances, including one which is called the ferromagnets, ferromagnets. Okay, they're basically done with iron because ferromagnets. These substances, once you have put an external magnetic field and you have oriented all the internal microscopic magnetic fields in the same direction, in ferromagnets, when you remove the external field, the magnetization inside remains. Okay, because the atoms are next to each other and they interact in such a way that they prefer to stay with this orientation than to go back to a random orientation. Okay, so this explains ferromagnets. What do you do if you want to magnetize a ferromagnet? You take an unmagnetized ferromagnet, you put it in a magnetic field to align the directions of the small magnetic fields inside, and when you remove the magnetic field, this remains magnetized. Okay, you have other, so this is discussed in the text. You have also other types of substances in which the magnetic field exists, the alignment exists when you have an external magnetic field, but it doesn't survive when you remove the external magnetic field. Okay, that's called a paramagnet. But this becomes now a bit specialized. Okay, and you have also substances in which the internal magnetic field is weaker than the external magnetic fields. So these substances are called diamagnetic, but it's the start of a whole chapter of physics. Okay, what I want you to remember for the rest of your life is that magnets work because electrons turn around the atoms. By turning, they are equivalent to small currents, and small loop of currents create small magnetic fields, which you can then influence with external magnetic fields, etc. Okay? Good. Okay. Now there is another law which I would like you to study, which is the Lorentz force. Okay, what is the Lorentz force? I will not go into details because you will forget the details, but I would like you to learn the principles. Okay, you remember that the Laplace force is given by this. Okay, the current times the length of the conductor times B times the angle between the conductor and the magnetic field. So if there is a force acting on a current, possibly, okay, there is a force acting on single charges. And now we would like to transform this law into a law which expresses the force acting on a moving charge. Okay, so the reasoning is here. I will not go through all that. You can read it if you want. This force, which we call the Lorentz force, this was the Laplace force, okay? This is Laplace and this is Lorentz. The Lorentz force, you see, this expression has been transformed into this expression, where here you have the charge, here you have the velocity of the electron, and here you have the magnetic field, and then the same sign. Okay, so this is going to allow you to compute the force which is acting on some particle of mass of a charge Q moving at a velocity V inside a magnetic field B. Okay, this is the Lorentz force. And if you compute the force like this, it's going to give you the force for a positive particle. If you want to have a better, a more careful expression, you need to put the absolute value of the charge. So it gives you the same intensity of the force, a positive intensity, whatever the charge is, and then the direction of the force, you are going to determine it with the right-hand rule. Okay? So in these matters, just to summarize, we have one formula which expresses the force on the current, but we can also derive a formula which gives you the force acting on a charge moving at a certain velocity. And you see, if the velocity is zero, if this charge is not moving, then what do we have? Well, the force is zero. Okay, so this is consistent with everything we said. magnetic fields and magnetic forces are generated by charges which are moving. If the charges are not moving, you will not have any effect. Okay? Okay, so I talked about the direction. If we want to know the direction of the force based on the direction of the velocity of the charge and that of the magnetic field, now we use the right-hand rule again, okay? But now the index will no longer show the current, the index will show the velocity at which the charges move. This finger will show the magnetic field as before, and the thumb will show the force as before. Okay? So let's do an example. I have a positron, so it's a positive particle, which is moving with the velocity to the right. And we have a magnetic field in this area, which is pointing, let me say it's pointing up. Okay, I'm drawing it like this to signify that this is an area in which I have a constant magnetic field. Can you tell me the direction of the force acting on this positron? I let you play with your hands a bit. So, velocity, magnetic field. The magnetic field now is coming up. So I have to go like this, okay? The velocity is to the right, the magnetic field is up, and so the force is directing downwards, okay? So here on this moving charge, we will have a Lorentz force, which is pointing down, okay? And so this particle is going to do what if this Lorentz force is pointing down? What do you think it's going to do? I am going to come to your homes and hit you personally if you don't talk. Okay? Personally, I will come and hit you until you understood that I want you to speak. It's going to do what? This particle, if it feels a force which is perpendicular to the velocity, it's going to start turning. No? If you are going straight and I pull you on one side, you are going to turn. Okay, so this particle, which feels the force, is going to start turning. Aha, it's turning, good. Now, let's say it's here, okay? The particle is here. The velocity is like that. Can you tell me now the direction of the force? You do the same trick again. But now I have to stand up, otherwise I will break my arm. Velocity is here. Magnetic field is up. Okay, so the force is again directed perpendicularly to the velocity. The force is directed like that. Okay, so the particle is going to continue turning. And as it continues turning, we can look again at the direction of the force when the velocity is in this direction. Well, the velocity is in this direction. The magnetic field is pointing up. So the force is now pointing again perpendicular to the trajectory. So what happens to particles, to charged particles which enter an area of constant magnetic field, is that they start turning, okay? The particles, if you have an area here with a magnetic field inside and this magnetic field is everywhere pointing up, okay? According to what we just said here, a particle which arrives here will start turning, turning and turning and turning, okay? And this is the basis of one thing we call the cyclotron. Have you heard of a cyclotron? You know what a cyclotron is? Cyclotron? This is the first type of particle accelerators which have been used at CERN, okay? that was in the 60s. Nowadays, they are in museums, these things. But I'm going to show you what a cyclotron looks like. A cyclotron, I guess we're going to find images from a museum. A cyclotron is this. Cyclotron. Let's see. Good. You see, this is one of the first cyclotrons. Okay, this is in California. This is another one, but now they are, of course, exposed in parks. Here you see it a bit better, this cyclotron. You see, this doesn't look very modern, okay? It's an old thing, okay? And of course, at that time, it was the top of the top in terms of research. So what do you see? You see my mouse? Hello, hello? Yes. Okay. You see here these red cables. These are the loops of wires transporting current. Okay, so we have a loop here and a loop down here. These are flat loops. I gave you even the expression to calculate the magnetic field inside. And so here we have large currents circulating, creating inside these loops a big magnetic field. Okay. And then inside these loops, now it's empty because this internal part of the accelerator has been taken out. This is the area where you inject your particles and they start turning. Okay, and you inject them in the middle, they start turning slowly, and then you accelerate them every time they turn. And in the end, they take speed, they take speed, they take speed. And when they are fast enough, you can eject them for the cyclotron. I don't know exactly through which tube it is. Maybe it is this one. You can eject them from the cyclotron at a high velocity, and then you can do particle physics by colliding these particles with other particles and see what comes out. So this actually is the ancestor of the accelerators we have at CERN nowadays. This technology was necessarily limited because if you want to increase the velocity of the particles with this, you need to make this apparatus bigger, okay? And you cannot do it huge. I mean, you cannot build something like that with 10 kilometers in diameter, because now the accelerators, they have 10, 20 kilometers in diameter, okay? So this is limited, okay? And this has evolved into other techniques. And I've told you the other day, when you have a big ring, you have a magnetic field to change the direction of the particles. You have electric fields to accelerate them. Here it was all in one. Okay? So, you have questions about that? Okay. So now this thing, as I told you, is accelerating particles, for instance, protons or antiprotons. And these particles, they are coming out here with a high velocity. And then what do? Well, we organize collisions, okay? CERN is trying to understand what elementary particles are made of. So they do it in a very basic way, which is they take two elementary particles, they have them collide with each other, and this collision produces some products. Sorry? Yeah, if you want, it's an explosion, okay, and then you have products which come out from this explosion. You have this explosion produces other particles, okay, because the shock contains more energy than the rest energy of the particles themselves. There is kinetic energy in there, and all this energy can be used to create new particles. So they make these particles collide, and then they analyze what is coming out. And one of the main tools which has been used about at the same time as the cyclotron is the bubble chamber. The bubble chamber, I hope I'm not, no, okay, there's no strange things in the bubble chamber. Let's take images of the bubble chamber. At CERN, we had a very big one. It's this one, I guess. It's the BEPS. the big European bubble chamber. Now it's in a museum. Now it's in a park at CERN in front of the theory division. And it's, you see, it's a thing which is like 6-7 meters high. It is a metallic enclosure, and inside this enclosure you have a liquid. I don't know exactly which liquid or a gas, it doesn't matter. What matters is that this liquid or gas is just at the point of boiling. Okay, it's at a temperature and at a pressure which is just before boiling. And you know, when something boils in your pan, I mean, if you warm up water, you see small bubbles forming on the bottom of the pan, and these bubbles come up. And I don't know if you have already noticed, but these bubbles, they form mostly where you have impurities, where you have dirt, where you have a hole in the pan, where you have some surface effects. Okay, and here is the same. We have inside the chamber this liquid which is unstable, which is about to boil, and we send into that chamber the particles which have been accelerated with the cyclotron. And what do we see inside the chamber? We see things like that. Oh God, what did I do? Okay, we see, yeah, but I would like to have the image. Thank you very much, but no, I don't want that. Oh God, now it left to a new page. Okay, let's take this image here. Okay, this is also an image of a bubble chamber. So you send your part. Yeah. Oh God. Okay, let's use this image. Okay, this is a view of inside the bubble chamber. I don't know if you notice there are windows through which you could do pictures. They were taking pictures at that time. Okay, in black is the gas in a pre-boiling state, and these white traces you see, these are particles passing through the bubble chamber, and since they are passing, they are causing this liquid to start forming gas, to start forming little bubbles. So actually what we see are very tiny bubbles of air along the trajectory, no, not of air, of the liquid, along the trajectory of the particles, okay? And so here, for instance, what do you see? You see this trace here, okay? It starts like this, and then it becomes smaller and smaller, and finally it becomes very small. This is just a particle which is stopping. Why do I know it is stopping? Well, the fact that it rolls up in one direction indicates the charge, because here I know the direction of the magnetic field. The magnetic field is either pointing up or down. I don't know. I cannot say it from this image. So the magnetic field is vertical. The velocity is horizontal. So the force will be perpendicular to the velocity. It will also be in the horizontal plane. If the particle is positive, it's going to turn in one direction. If the particle is negative, it's going to turn in the opposite direction. So with this kind of detector, you can tell what the charge is of the particles which are produced. Okay? And so you study the charge, but then the mass also plays a role in the size of the circle, etc., etc. Here you have a phenomenon. You see the tip of my arrow of my mouse here? Yeah. Okay. What do you see there? You see nothing, and suddenly you have two particles leaving like a V. Well, there some disintegration process took place. And I guess there was a photon arriving. A photon is not deviated because it doesn't have any charge. A photon is a grain of light, if you want. Okay, and then this photon disintegrated maybe in positron and electron. I'm not sure, but if it's that, they should turn. I don't know the interpretation of that image. Okay. But these are the first images people were doing in particle physics, and the determination of the characteristics of the products of a collision, they depend crucially on the existence of a magnetic field. Okay? I can show you other pictures of these bubble chambers. Well, they all resemble each other. Okay, here you have another one. Okay, you also see, oh God, that I'm tired of internet. Okay, this picture here, you see, it's another picture in which particles are arriving in this direction. Then you have here, I don't know what this is. You have some particles which you don't see until here, and suddenly they must be decaying, and they stop miserably in a small circle. Why is the circle becoming smaller? You understand that? Because initially the velocity of the particles has a certain value, but these particles now are crossing this medium, which is a gas or a liquid, and so they have collisions with the atoms of the gas or liquid, and due to this collision, their speed decreases, and if the speed decreases, the force decreases, and so the radius of the circle becomes smaller. Okay. Sorry? Yeah. Uh, Let me find an image for you. Um, okay. You know what quarks are? A quark uh, is a component of protons and neutrons. Okay, protons and neutrons, they are made up of three quarks, which are linked in a certain way. And if you want to study quarks, then what do? You take protons and antiprotons and you run them against each other. You make them hit at a very high speed and you see what is coming out from the collision. Okay, what they do at CERN is not very smart. I mean, if CERN was not studying elementary particles, but let's suppose that CERN was studying nuts. Okay, nuts, des noix, the fruit, the noix. Okay, let's imagine you cannot open a nut, but you want to guess what is inside the nut. You want an experiment to tell you what is inside the nut, but you cannot open it. Okay, so what do? Well, you can accelerate nuts uh, against each other at very high speeds. You provoke collisions, and then all around the collision area, you analyze what comes out. And then you try to reconstruct the center of the nut based on what you saw as the result of the collision. This is basically what they do at CERN. Okay, I said it's not very smart. This is not true. This is the only way you can do it with elementary particles. Okay, so let's imagine, okay, this must be an image, CMS, I don't know. Okay, this is an image of one of the experiments at CERN. I'm not going to go into details. You see that these images, they are now of much better quality than the images we saw in the bubble chamber, because now we have other technologies to understand what is going on. But basically, it's the same. Basically, you have here a collision area, so the beams of particles, they are coming in this direction and in the opposite direction, and they meet here. And when there is a collision, you have an awful lot of products coming out, and you analyze this product, and you see that these products, you see that they are turning, okay? But this is higher energy, so they go faster, so the radius of the circle is bigger, but they are turning. And so according to how they turn, you can determine their electrical charge. And you can also compute the mass in some way. And then we have inside these devices, these are multi-devices with different layers recording different things. We also have calorimeters. A calorimeter is a device which measures the energy. Okay, so you determine the energy of the particles, the velocity, the charge, the mass, and so you can identify these particles. And you can try to understand what went on during the collision, and you can try to understand what your protons are made of. Okay? This is CMS experiment. Okay, let's go see CMS. CMS detector. How the hell is this made? The CMS detector. Here it is. I'm not a specialist of CMS, but we will make it to understand that drawing. Okay, come here. Where is the image? Okay, this is the detector. Now the scale of the detector is given to you by the size of this guy. Okay, so it's a bit bigger than the cyclotron, which you could put in a room. These detectors, they are around the collision areas at CERN. Here in the middle of the detector, you have the collision area. You have packets of particles arriving in this direction and from the other direction, and they meet exactly here. And then around the collision area, you have different types of detectors. You have the blue one in the center, which is a crystal electromagnetic calorimeter. So crystal means it's not liquid, it's done with crystals, but it's a calorimeter, so it's able to measure the energy. Inside here, we have silicon trackers. These are devices in which when a particle passes, it leaves a trace. Okay, now we have modern things. Anciently, what they would do is that they would pile up thousands of pages of photographic paper, and then a particle was passing through, was leaving a trace, and then they would take apart all these layers of photographic paper and study how the particle moved in 3 dimensions. Okay, so you have all kinds of things. You have also chambers containing electric wires in different directions, so you can tell where the particle went through. So all this shit which is around the collision area serves to identify the products of the collision. Okay, and the magnetic field is something key in this kind of things, because you don't do any particle detection without a magnetic field. Okay, now what else did I want to show you? Yeah, this is what it looks like in reality. You see the center of the detector. These are two pieces which go one into the other. The center of the detector is extremely dense in terms of apparatus of measurements. Okay, I don't know. Have you visited CERN? Yeah, well, maybe that you couldn't see. This is stuff you can see when they do maintenance of the equipment. Okay, you see here the size of this thing. It's CMS again, and you have the various detecting layers around the detector, around the collision area. Okay, Ali, let me go back a bit to all that. Okay. Now, the last thing I want you to do, because I want to leave you an impression of understanding things a bit, of knowing where things come from. I'm not going to go into details of CMS, etc. One thing I would like to go into some details into is the electric motor, because this is the most important application for everyday life of what we've been doing until now. Okay. And an electric motor, I will take an extremely simplified model of an electric motor, but it works. And I will explain you now how an electric motor works. It's a very simplified model because inside a normal electric motor, you have lots of loops of wire around things. Here we take a very simple electric motor. We take just one loop of wire. Okay, so we take a permanent magnet, and this permanent magnet has a north pole here and the south pole here. The north pole is red, the south pole is green, and since it's U-shaped, you have one pole at one end and the other pole at the other end, as usual. Okay, the poles are at the ends of magnets. But in this way, by folding the magnet, you can have the poles in front of each other, facing each other. And so you have a magnetic field which is here vertical from the north to the south. So the magnetic field is pointing downwards here. Okay? Good. Now we have a wire inside this magnetic field, and there is a current going through this wire. This is the current you give to your motor to make it work. Okay, so now you make the current turn. I'm sorry, I don't see with my glasses. Yes, the current is now turning in that direction. Why is it turning in that direction? Because here there is a connector which connected to the plus pole. Okay, so you have the plus pole of the generator, current comes here. Here there is a device distributing the current. For the moment it's connected to this wire, so the current goes like this. Good. Okay, we have a current to the right. We have a magnetic field which is going down. Sorry, I put my hand like this, okay, with my middle finger pointing down. So the force is going this way. Indeed, the force is here noted. It's a small arrow which you have there. So this is going to make your motor turn this way. Okay? And then it's going to turn a bit, but here soon it will no longer turn, because if this loop of current is horizontal and the force is horizontal, it's not going to turn. Okay, so that's where this, sorry, it's turning like this. You want me to do a bigger drawing? Well, you have this loop which is like this. Okay, the current goes this way. You have a magnetic field which is vertical pointing down. Okay, so the force, the magnetic field is pointing down, sorry. Okay, so I should put my hand like that, and the force is going to go down across the page. The force is going to go down here across the page. So I'm looking at this motor from this side, if you wish. Okay, so this is going to make this thing turn like that. Okay, and down here, what happens? It's magic, because down here the current is going the other way. If the current is going the other way, the current is going like this, the magnetic field is still down. Now the force is going up. Okay, so down here I have a force which is coming out of the page. Okay, and so this part, if this part is going down inside the page and this part is coming up, of course it starts turning, right? But now the problem is that if you do it like this and you don't change the direction of the current, it's going to turn until it's in the flat position, and that's it. It's not going to go further. So here we have a system which distributes the current to the wire. And you see that this thing, it has one part which is up here, which is connected to the plus, and one part which is down here, which is connected to the minus, and between the two there is no contact. It's an isolator. Okay, so when the wire becomes horizontal, there is no more electric current which is sent into the wire. The wire continues turning because it has started to turning, so it has an inertia, a mechanical inertia. It continues to turn until it's in that position. And in that position here, this thing which distributes the current, it has turned, okay, because it turns with the engine, with the loop. Now, this part here is connected to the plus, and this part here is connected to the minus. So we are in the same situation as that, except that the wire has not done one turn, but 1/2 turn. But since we have inverted the direction of the current inside the wire, the forces are still in the same direction. Okay, they are still like that, and so your motor is still going to turn in the same way. Okay? This is the basic principle of an electric motor, and it's based on these laws which I explained you. Now, of course, if you take a realistic electric motor, let's take some image of that. Okay, if I take a realistic electric motor, it's going to look very different, because the motor I showed you is not a good motor, it's not efficient. So if you take a realistic electric motor, from the outside it looks like this. Okay, you saw that, you saw many of these, and on the inside it looks like that. Oh God, Ah, the, if I was the chief of the world, some things would change and internet would change. Okay, so let me look for the inside of an electric motor. Which one am I going to use? No, it's okay. Let's try this one. You see this motor? It is much more complicated than the one I showed you before, but it's based on the same principle. Okay? Well, but you don't see it well on this image, Samuel, because the other day with the other class, I had found a very nice one. Yeah, this one. Okay. This one. Okay. What do you see? Well, you don't see much. You see that here you have cables around the part, so there is a rotor, which is the part that turns, and a stator, which is the part that doesn't run. Okay? Around here, you have cables. You see these cables? These are big cables, okay, because the current is intense. So these cables are there. They are wired as loops, and they produce the magnetic field that the motor needs. In our simple motor, we have a permanent magnetic field. Here we have a magnetic field produced by currents. And inside, instead of having just one loop, you have many loops, and you have many parts creating the magnetic field. Okay, and then you have somewhere a device which distributes the currents to all these parts. But again, I don't like this image so much. This one, maybe you see it better. There's something against me today. I don't know. Yeah, it was this one, I think. Okay, now you kind of see it. You see the part which was distributing the current. In our case, it had only two sides. It was either giving the current to one side of the loop or to the other side. Here we have like 20, okay? And each of these contacts is connected to one magnet, which is here, okay? And this magnet is surrounded by electric wiring, okay? And around this part which turns, you have the wires creating the magnetic field outside, okay? And you see here these parts, these are where the contact is established between the electricity arriving from the wall, okay? This is where the electric power arrives to the motor, and here it's distributed to the contact which is just in front of it. These things, they are called les charbons. I don't know if you heard, when you have an electric engine, it usually lasts very long, but these things, they are getting damaged because there is a strong friction there. So these things, you have to change them from time to time, and it's done a bit, it's a material which is like pencil, and so it's called the charbon. Okay, it's black. Okay, so that was for the electric motor. And now, what is a dynamo? Well, a dynamo is it's exactly the same as an electric motor. Okay, it's built the same. Now, if I type dynamo, yeah, I have to be careful because there is a rock group called dynamo. So if I'm not careful, it will give me the images. Okay, if you see, I type dynamo and it gives me basically the same images, because a dynamo is the same as an engine. If you take an electric motor and you don't give it electricity, of course it's not going to turn by itself. But if you make it turn, it will produce electricity. Okay? So if you want to produce electricity based on some mechanical power, then for instance, you have water coming down from a dam. This water forces a turbine to turn, and then the turbine is connected to the dynamo. The turbine makes the dynamo turn, and the dynamo, while it turns, produces electricity. This is how we produce electricity nowadays. Okay, so it's a totally basic thing, and it's a pity, by the way, that we didn't base our economy more on the electric motor rather than on the explosion motor, because the explosion motor is destroying our planet, while the electric motor would not have done much to the planet. But that's the problem when people make choices according to what they will earn in terms of money, rather than in terms of what humanity will benefit from it. So in the 19th century, people wanted to make money with oil, and they developed oil, and they supported the development of gas engines, and that's where all the mess we are in now started. If we had gone ahead with the electric motor, probably we would not be at this point today. But, well, if I was the chief of the world, that would also change. Okay, so the dynamo basically is the same principle. Okay, you have a wire which we now oblige to move inside a magnetic field. As a result, we have a force acting on the electric charges, and so these electric charges, they start moving, and by moving they create an electric current which we can measure and use. Okay, isn't that amazing? Okay, listen, it's long. I took longer than usual. What I'm going to do next week, because next week we are supposed to continue the courses. Okay. The parallel class is done because I had them on Monday, and next Monday is a holiday. But you are not done. So next Monday there will be a course. And if you come to the class, and I guess you are all good boys and girls, so you will come, what we will do is practice all that. Okay, I have a set of exercises. I have 3-4 pages of exercises. We are going to work with these notions, with these formulas we saw today, and measure the force acting on a wire, measure various things like that, which are kind of interesting. Okay? So if you want, what you can do for next week, it will be June 2nd. You can start doing these exercises. You can do them all if you want. I mean, you do how many as you like. And we will do that next week. Okay? Good. Have a nice evening, and thank you for participating so widely. Let me just see how many we are online. Where is Google Meet? It's here. Okay, now there are 11 online, no 10. Okay, it's the same as what I wrote before. Okay, bye-bye. Bye-bye. Bye-bye.